So I'll probably delete the other ones except for that one. Tomorrow you will get the new packet. I don't know if we'll have a new packet day song or not. We'll have to wait and see. But that packet will have this page. If you printed the one out today, it won't have this. But I just want to quickly review valence electrons. So if we recall all the way back to 6th, 7th, 8th grade, somebody gave you something like lithium with 3 protons. Therefore, we have 3 electrons. We have 2 there, and we have 1 here. Now, if you have your periodic table, that's going to be an asset for you today. This is why lithium is in group 1A, because it has 1 valence electron, right? The first ring has 2. The next ring, we say, always has 8 and 8. We'll see why that is later. Fluorine is the other element we're going to deal with, so we see it's in group 7A. So we can expect it to have 7 valence electrons. Fluorine has 9 protons. Therefore, it has 9 electrons total. There's the first 2. 2 from 9 leaves us with 7. Now, this is a metal and this is a non-metal. The ionization energy here is low. If we look on the periodic table, the electronegativity here is high. Fluorine is going to take that electron, giving it 8, giving this 2 here. And that's going to fulfill something we call the octet rule. The octet, if it's the first energy level that we're dealing with, just 1s, it can be filled with 2. I know that's not an oct, but that's the first energy level. Every other one, a lot of teachers always said 8 and 8 and 8. That's because we're only worried about the S and P. The 2 and the 6 there, which is a total of 8. As we can see that the fluorine has here. It's become fluoride. This has become a lithium ion. Electrostatic forces are going to connect these two into what we call an ionic bond. Metal and non-metal. Hey, hold on, I have to get something real quick. So, that's ionic bonding. It's based off of this octet, right? We could do this with lithium and oxygen. The thing you're going to find out is that oxygen has 8 protons and therefore 8 electrons, 2 and 6. So instead of gaining 1, it's going to gain 2. Well, that's going to take 2 lithiums for every 1 oxygen, right? We did that a lot whenever we named all of these things. Metals and non-metals, you just name this like this, lithium oxide, right? Now we want to get into those things like, for example, dihydrogen monoxide. This is called covalent or molecular bonding. We're going to draw a Lewis structure based off of that. So instead of looking at oxygen like this, to understand the concept, it's easier to look at oxygen like this. 1s2, 2s2, 2p, what do we got? 2p6. No, I'm sorry, 2p4. There we go. So we have these guys. 1, 2, 3, 4. 1, 2, 3, 4. And we have 2 unpaired electrons here. If we look at hydrogen, hydrogen simply has 1s1. Now the cool thing is we really said that we can do this any way we want. So I'm going to go ahead and make this a down arrow. Now I'm going to say there's actually 2 of these. If we see these hydrogens and these oxygens together, they can make water. And notice that this bond is written between the 2 atoms. That's different than here, where the electrons are transferred. Let's imagine that these are those electrons. We have one from the oxygen and one from the hydrogen. That is what we call a pair. And this is called a shared pair of electrons or a bond. Notice that the hydrogen has its 2 electrons, 1, 2, because it's sharing that one from the oxygen. The oxygen has 4, but don't forget, we don't care about these because these are close enough to the nucleus they don't count. The oxygen also has this pair and this pair. 1, 2, 3, 4. These are called lone pairs. They're only from the oxygen. So 1, 2, 3, 4, 1, 2, 3, 4. And then one of these and one of these is from the oxygen. The hydrogens here bring their 1 electron to make a bonding pair. And that's molecular bonding. A man by the name of Gilbert Lewis came up with this so that we could kind of visualize this. The key things that you need to be able to do is find the valence electrons. So another way to do that is to use your periodic table. For example, if we have P, there are 5 valence electrons there. And we have H, there's 1 valence electron there. So if you did print it out, that brings us to the counting electron spot. pH3. We said 5 and 1. But there are 3 hydrogens, each with 1. That is a total of 8 electrons. If we look at phosphorus, that is going to be 3s2, 3p3. So we have 2 and then 3. Each hydrogen has the 1. We know that these are going to bond up. Each hydrogen is going to be 1, and it's going to pair with these 3 electrons in the p's. 1 from the phosphorus, 1 from the hydrogen, 1 from the phosphorus, 1 from the hydrogen, 1 from the phosphorus, 1 from the hydrogen. That's 2, 4, 6. If we subtract that, there are 2 electrons left. Only valence electrons are showed in what's called a Lewis diagram. We have 6. Each of these hydrogens have their 2. The phosphorus has these 3, but don't forget, it also has these s2. So 2, 4, 6, 8 for the phosphorus. There's its octet, and each of the hydrogens have their own octet. Where did I get these numbers? From the periodic table. That's their group number. Right? 1, 2, 3, 4, 5 for the phosphorus. 1, 2, 3, 1 for each of these hydrogens. So the phosphorus here has 3 bonds and 1 lone pair. That's going to be important later for the shapes of these. Then it says, okay, do NH3. And all it wants you to do, this drawing, that's where we're getting to. All it wants you to do in this section, exercise 1 here, is to just tell how many valence electrons each one has. You do this by looking up on the periodic table what the groups are, multiply them by the subscript, and then add them together. SO2, for example, we have 6, and we have 6 times 2. 6 plus 12 is 18, right? And it goes on and on and on there. So you can complete that when you get the packets tomorrow, hopefully, or if you printed them out, you can complete it now. Then it talks about drawing the structures. So let's try that. This is on page 4. It gives us HF. That's all it's going to give us is HF. We have to count up the electrons, group 1A, group 7A. There's one of each. 1 plus 7 equals 8. That's the total number of valence electrons we can play with. There is no 1 to put in the center because it's just 2 elements, or 2 atoms, I should say. So we will combine them like this. The hydrogen has its octet completed. 8 minus 2 gives us 6 left over. Well, the fluorine needs 6 as well. So here's 2, 4, 6, 8. There's the octet for the phosphorus. Questions? Nitrogen triiodide is the next example it gives you. So the first thing you'll do is you'll count these up. Anybody got the number for it? 5 plus 3 times 7 is 26. There's only one thing that can really go in the middle here because there's only one nitrogen. It would go in the middle. Iodines all around. That's 26 minus 2, 2, 4, 6. That's 20 electrons left to go around. None of these are hydrogen, so each of these are going to actually need a total of 8 around them. Here's 2, 4, 6, 8. 2, 4, 6, 8. 2, 4, 6, 8. 2, 4, 6, 8. We just put 20 on, watch. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. And then we have the 2, 4, 6 that we already took away from here. So that is what we have. Then we would tell how many bonds are on the central atom. 1, 2, 3. And there is one lone pair. All right, on your scrap paper, let's try one. CCl4. Go ahead and try CCl4. I'll give you a few seconds to do that. This is in group 4A. This is in group 7A. You should have 32 electrons that you're able to use here. 4 from the carbon, and then each one of these is bringing 7, and there's a total of 4 of them. That's 28. Carbon will go in the middle, since it's a unique element. Cls will go all around. Just this part is called a skeleton structure. When we put all the rest of the electrons on, it's going to be the Lewis structure. Currently 2, 4, 6, 8 are being shown. 32 minus 8 gives us 24 left over. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32 total electrons. The carbon here has 4 bonds in 0 lone pairs. Questions there? NH3, group 5, and group 1, so that's a total of 8. Nitrogen in the center, since it's unique. 1, 2, 3. 2, 4, 6 total electrons. 8. We can draw lone pairs as either dots, as I did here, or as just a line. Bonds are often drawn in lines. You don't often see those as just dots. How many bonds, how many unshared pairs? Student of the month question.
3 and 1.
Nice. 3 bonds, 1 unshared pair, or lone pair. Let's try one more thing. Oxygen, O2. How many electrons will we be able to play with O2? Anybody? Find the group that oxygen is in and multiply it by 2. What do we get?
12.
Very good. It's in group 6A, so that's a total of 12 valence electrons. We don't have a central atom, so we'll put oxygen there. There's 2, so that gives us 10 electrons to play with. We fulfill the octet for everybody. 2, 4, 6, 8, 10. Oh no. That's 12, 14 total. Well, 14 minus 12 means that I'm using 2 extra electrons. Anytime you have extra electrons, you need another bond. In this case, it's only 2 electrons, so somewhere in this we're going to have a double bond. If we put a double bond in this, right, there's 2, 4, and we can only go up to 12. 2, 4, 6, 8, 10, 12. This has too many. So we know that this won't work. This must be the Lewis structure then. We take away 1 from each side and we put a double bond in there. Now, a teacher may have told you a long time ago that oxygen likes to have 2 bonds. This is true. We have a rule for this. It's called HONC. H-O-N-C. Hydrogen and halogens like 1 bond. Oxygen likes 2 bonds. Nitrogen likes 3 bonds. Carbon likes 4 bonds. You can memorize this rule, or you can simply look at the idea. There's the box for hydrogen. 1, 2, 3, 4, 5, 6 for oxygen. 1, 2, 3, 4, 5 for nitrogen. Here's the only time it gets weird. We have 4, carbon is in group 4A, but instead of being bunched up here, they create what's called sp hybridization, where each one of these, when it bonds, gets 1. And that's how we get those 4 bonds for that carbon we saw up here. Sometimes we call this looking into the future. If you know this, and you have a compound, you can look into the future and say, I bet that that's going to have something that's different than I'm used to. If we were to draw nitrogen, and we know that nitrogen likes 3 bonds, oxygen had a double bond here, so what do we expect nitrogen to have? Anyone? Well, let's count it out. That's a total of 10 electrons, right? 2, 4, 6, 8, 10, 12, 14. How many are we over this time? We're 4 electrons over. That means we need 2 more bonds. Well, there's only one place that we're going to be able to put these bonds, and that's between the nitrogen. It's no mistake that most of our atmosphere is made up of nitrogen, because it's very difficult to break these 3 bonds. 22% is made up of oxygen. It's difficult to break this double bond. It's way more difficult to break 3 bonds. Way more difficult. One more student of the month question. Why did I draw this like this? I could have taken this and just drawn it like this. Or I could have taken this and drawn it like this. Or this. But why did I choose this one here and this one here? Anybody? True student of the month question here, huh? Plus you have the anxiety of having to press unmute and talk.
Does it show the bonds?
It definitely shows the bonds. These are always going to show the bonds. And it shows the lone pairs. But let's think about this, Thomas, since you spoke up. What are the charges of all of these things in these lines?
Negative?
Yeah, and if all of these negatives are around each other, what are they doing constantly to each other?
Pulling each other in?
Are they pulling each other in or pushing each other away?
They're pushing them away.
Yeah, right? You caught yourself. So take a look here. Instead of drawing this like this, it's going to push them away. Instead of drawing this close to this, it's going to push them away. This is called the valence shell electron pair repulsion theory. Valence shell electron pair repulsion. This is going to help us figure out the shapes of these later. 3 bonds and 1 lone pair has a particular shape. That's for another day. The assignment for Friday by 3:45, guys. I'm sorry. Yeah, Friday by 3:45 or whatever time school's over, is to turn this in. These 4 problems right here. If you don't have them now, you can take a picture and you can write it on regular paper, or you can wait until you get it tomorrow. But all I want you to do is draw the Lewis structures and then tell how many bonds and lone pairs each one has. And if you have questions, by all means, you can stick around. But at this point, you have your lunch and the rest of period of 6-8.
What page is that on?
This is page 13 on the like the big one, and it should probably still have those page numbers, maybe. But it should still be, if you just printed out the shortened one, yeah. Otherwise, you can take a screenshot of that real quick and just get it however you need. If you want to stick around, by all means,